In our last class, we talked about few definitions related to cryptography, for example, cryptography as well as cryptanalysis, then cryptology. And as a part of cryptography, as I mentioned, we had symmetric cryptosystem as well as asymmetric cryptosystem. The another name for symmetric key is private key cryptosystem, because here these two keys, they are supposed to be the same, as I mentioned in my last class. Whereas in asymmetric crypto system, or there is another name called public crypto system, these two keys will be different. Okay. So for example, for symmetric crypto system, we will have AES and RC4 that we will study in our syllabus. So AES is a block cipher and RC4 is a stream cipher. So at present, you might not be able to understand what do you mean by block cipher or stream cipher. But later on in our course, we will study all of them. On the other hand, for asymmetric crypto system, we do have RSA, Elgamal, and there is another scheme called Rabin crypto system. So we will do all those things. And this part, RSA as well as Elgamal or Rabin crypto system, they require uh, prerequisite of mathematics, mostly abstract algebra as well as number theory. So in our course, we will cover all of them. So in my last class, I have already talked about this Catalan cipher and then Caesarean cipher. So you can understand both of them. They were used quite long ago. It's a 50th century BC, and this is 50 BC, 50th BC. So long back, more than 2000 years ago, these schemes were used. And then we have explained how mathematically the schemes could be explained. And then I talked about few attacks, mostly the exhaustive search attack on Caesarean cipher, or another name is Cipher. Then we talked about a scheme called affine cipher, which does have the key space quite significantly larger than the cipher or Caesarean cipher. For example, in case of a Caesarean cipher, the size of the key space was 26, whereas in affine cipher, the size of the key space was 312, that we have already seen. Then we have extended our scheme to by using the symmetric group or the permutation group by saying another scheme that was known as substitution cipher. So in case of substitution cipher, we have seen that the key space was significantly large and the size of the key space was 26 factorial. So it's a huge number. And as you can understand, we have shown by using a simple example, like if we have a decent machine that can handle 1 million, that is 10 lakhs of cipher alphabet per second, to do a exhaustive search on this scheme, it will take around 10 to the power 13 years, 10 to the power of 13 years, which is more than this time is more than the age of the universe. So you can understand that exhaustive search is quite impossible by doing this by using some machines. But as I mentioned, cryptography doesn't always follow the linear path. So there could be plenty of other methods to which you can solve this problem or attack this scheme, out of which frequency analysis is one of such scheme. Every language, not all the alphabets are equally likely. I mean, they do not occur with equal frequency. For example, if we consider the starting alphabet of the names of Bengali people, like all men or women, if you look at the starting alphabet would be mostly it starts with S. So in my last class, I have already shown in the last class even out of this 20 students, you might have 7 students whose names start with S. Also, T as well as A are quite popular for Bengali people to have their names starting with A, T or S. So you can see that around say more than 40% of the names will start with A, T or S. So that means for Bengalis, this A, T, and S, they are mostly used alphabets in case of naming of some person. Similarly, if we look at in a broader sense, if we look at in English alphabet, then it has been seen statistically that E is the mostly used alphabet. then T is the second mostly used alphabet and A is the third mostly used alphabet, and so on. Similarly, we have also seen that there are pair of some alphabets, for example, TH, HE, IN, etc., which are in a decreasing order. So TH is the most popular or mostly used alphabet in pair. Similarly, HA is the next most popular alphabet used in pair. Similarly, we can have THE where three alphabets together. This is the most popular or most frequently used alphabet thrice in together, and so on. So based on that attack, frequency analysis can be made. In my last class, I have explained in detail, and this could be done. So till now, whatever the schemes that I have mentioned to you, so here A is say a sender and say he is sending some message to another person B using some symmetric key. So what does it mean? Symmetric key, for example, in case of Caesarian cipher, what we had k equal to some value, say 11. In case of affine cipher, we could have k equal to an ordered pair, say 11 or and maybe say 20. In case of permutation cipher, we could have a permutation pi of some 1, 2 up to 26 and say 3, 4 and then maybe 1. So this is a permutation. So they are the keys. They are the keys. And suppose this guy wants to send some message to B, then both side they will should have this same key. So in case of Caesarian cipher, B also use k equal to 11. In case of affine cipher, both B will also use the same key. Similarly, in case of permutation cipher, both sides they are going to use the same key. So say here just now I have mentioned the same key should be used in both sides. That's why they are called symmetric key. Symmetric key cryptography. There is another name. This is also known as private key cryptography. Private key crypto. So why this is called private? Because these keys have to be known only to this A and B. So they must store or they must keep these values of these keys secretly, or they should keep it private. They should not make it public. Whereas if somebody, some opponent, they are going to hack or they are going to intercept this message, then what they will get? They will get the cipher text. Now the question is, from cipher text, how the opponent will get some information about the plain text or the key. So as I mentioned, so in case of these two, the exhaustive search, that means start with all the possible keys and try to explore all possible keys. In that case, exhaustive search could be very easy, but here if you attack it with exhaustive search, then you will have to search around 26 factorial many options, and that is quite infeasible. But we have already seen there could be other way, that is known as frequency analysis, through which the people may get information about the plain text. Okay, but in all this case, if you see that there is one kind of special property. For example, if I consider this Caesarian cipher, suppose k equal to 11, if A is in the plain text, then by shifting A 11 times to the right, whatever be the alphabet, say X is the alphabet, then wherever I will have A in the cipher text, that A will be replaced by the fixed X. Similarly, in case of affine cipher or in case of substitution cipher, the same thing will happen. That means a particular alphabet, for example X, that will always be shifted to a fixed alphabet, say capital X, and that will be fixed once these keys are fixed. Okay, that's why this frequency analysis takes into play. Why frequency analysis works? Because in case of cipher text, if you have a cipher text And what you need to do, you need to just check only that how many times which alphabet occurs in how many times. For example, you will consider all the alphabets and checks A how many times it occurs, B how many times it occurs, etc. And D and XYZ how many times they occur. So if what is the conclusion? Suppose you see that B is the most occurred alphabet in the cipher text, then it is highly possible that B is actually E in the original plain text and so on. So it happens because wherever I will have E, that must be replaced by B and so on. So that would be a kind of trial and error method through which you will be able to find the exact correspondence. But all these schemes, what is happening, the plain text will always go to a fixed cipher text. A plain text alphabet will always go to a fixed cipher text, and this kind of schemes are known as monoalphabetic. Monoalphabetic scheme. Alphabetic scheme. So it's quite important. So these schemes are monoalphabetic. Okay. But if your scheme is monoalphabetic, then frequency analysis could be a possible choice for your attack. So people were thinking of why not we should have a scheme in which the same alphabet, say X, will go to some different alphabets in different occurrence of the key. For example, sometimes it will go to A, sometimes it will go to P, sometimes it will go to X, and sometimes it may go to Z. And if this happens, then you can understand that frequency analysis is no longer valid, because you then won't be able to count how many times the maximum occurrence of a particular alphabet, because that may come through different alphabets. Okay, so that gives the idea of polyalphabetic cryptographic scheme. Polyalphabetic cryptographic scheme, crypto scheme. So let us have some example how it happened. Okay. So this is an example known as Vigenere cipher. It happened around 1586. So it was a polyalphabetic cipher system. How it works? So suppose cryptology is my original plain text. Okay. Now here this is, suppose CIP is my key. Okay. Let us have a look. So cryptology I have written, and the corresponding key I just repeat many times, like CIP, then again CIP, then again CIP, and since there is one left, so I just put C. Now the question is how the ciphertext is made. Idea is very simple. Just like Caesarean cipher, what is the roll number for C? If you remember, the roll number for C was 2. Why? Because it was like this: A, B, C, D, and so on to X, Y, Z. And it starts with 0, then 1, 2, and then it ends with 25, 24, 23, and so on. So you can understand the roll number for C was 2. So I just write, in case of this plain text, C means 2. Similarly, R means 17, Y means 24, and so on. And again, in case of C, what was the roll number for C? C was 2. Then I, the roll number of I was 8, and then P was 15. And then I repeat the same thing, 2, 8, 15, 2, 8, 15, and it's only 2. Okay. Now I just do addition modulo 26. So 2 plus 2 is 4, this is 25, and this is more than 25, right? It's more than 26. So how it's happening? It's 39, and 39 modulo 26 is 13. Similarly here 17, then it's 27, and modulo 26 becomes 1, and so on. So now the roll number corresponding to my ciphertext is this. As a result, if I just shift it over the as ciphertext, then the roll number for E was 4, and Z, so 25 was Z, M, and so on. So this is my ciphertext. Is that clear to all of you? Now, if I ask you, can you just explain mathematically, though at the time of Vigenere, it was not there, but if I now, since you have the plenty of, proper idea of group, ring, and field, so can you just explain how this is happening? So my plain text was cryptology, cryptology, and my key was CIP, then CIP, then CIP, and again C. And then I get some ciphertext. Now, can you explain what is my what is my P? That means set of all plain text. What is my C? Set of all ciphertext. And what is my key space? So this is called key space. This is called plain text space. This is called ciphertext space. And what was my encryption function? And what was my decryption function? Anybody? Can you please try? So what is my plain text set here?
Z26.
Somebody says Z26. Now, what is then your ciphertext?
It is also Z26.
And what is your key space? Now it will be a difficult task for you to say what is the key space then. What is your key space? Now you can understand the key was CIP. It's not only C, it's CIP. So it's basically an ordered tuple, right? So what was the encoding CIP? It was 2, 8, 15, right? So it was 2, 8, and 15. So my key is basically a tuple, right? So it's basically Z26 whole cube because this belongs to Z26 whole cube. Now tell me what was your plain text space? What is your ciphertext space? Key space I have already given. Now what is your plain text space? Tell me. So the key will be acting on what? Acting on plain text. Now if your key space is Z26 whole cube, so in one go, it will also act on three plain text simultaneously. That's why it is Q. That is why ciphertext will also be Q. Because your ciphertext will be at a time this, and your plain text is at a time this. Okay. That's why P, so it is for M positive integer. So in my example, M was 3. As a result, C, P, and Q, K are Z26 to the power M. So in my case, M, the value of M was 3 here. Okay. And how it works? It works basically in a simple way, like Caesarean cipher. So how it works? So E of K, suppose your K is 2, 8, and 15, and it works on some plain text, and this plain text is an tuple, say M1, M2, M3, and it gives you how it works. It works like M1 plus 2, M2 plus 8, and M3. So it was 3, M3 plus 15, and all of them they are in Z26. So that belongs to Z26 cube. Okay. So it M1 plus 2 means actually they are elements of Z26. So as a result, this means M1 plus 2 modulo 26, M2 plus 8 modulo 26, M3 plus 15 modulo 26. So that happens. Now you can understand that, is it a generalization of Caesarean cipher? Can you say that this scheme, this Vigenere cipher question is Vigenere cipher is a generalization of Generalization of Caesarian cipher. True or false?
True, sir.
Why? Why true?
In that case, the key will be only Z26.
Okay, so in that case, basically it should not be over k. In that case, m should be 1. If your m is 1, then automatically the k as well as this k. So this k, this m will be basically 1. If that becomes 1, then that becomes automatically a Caesarian cipher. So in that case, this will be only 1 and you will have only one coordinate. And that coordinate will basically the same as it will be only 1 and the same as Caesarian cipher modulo 2. So in that case, what you understand is this is basically a similar idea of Caesarian cipher. But what is the key space size here? What is the size of the key space here? What is the size of the key space? Can anybody tell me? What is the size of the key space here? It's quickly.
26 cube.
Yes. So 26 in general, in this particular example, this is 26 cube. You are perfectly all right. But in general, if I consider it in terms of m, then this is 26 to the power m. Okay. So this is quite big than the Caesarian cipher. Now our question is, how can you attack on this? Okay. How can you attack on this? So question, how? So this is your homework. How can you mount an attack on Vigenere cipher? Okay. So is there any better method than exhaustive search? So you need to find. And you may also try to, so that would be your, so first on C programming or any other language if you prefer, the first would be implementation of Caesarian cipher, then implementation of affine cipher, and then implementation of this Vigenere cipher. Also make an attack, make attack on it, on them. So that will be your programming language homework. So you can use any of the programming language, whatever you feel comfortable with. For example, C, C++, Java, Python, whatever. So in today's class, I will also explore with you an example of uh, uh, another uh, kind of package. This is known as Sage Math. Sage Math. So you can also try the same thing with using this Sage Math software. Okay.
Sir,
So up to this, any question? Yeah.
affine cipher or substitution cipher or Vigenere cipher, they all are basically generalization of Caesarian cipher.
Yes, but they yes. So in my last class, I have already mentioned about it. In substitution cipher, if you put uh, so you can understand it's a basically for Caesarian cipher. If you put k equal to 11, that means something is shifted, and that means A goes to say some X, B goes to some Y, C goes to some Z, and so on. Okay. So that means you can also consider that shift also has a is a kind of permutation. So in that case, substitution cipher will be a generalization of Caesarian cipher. Similarly, in case of affine cipher, it was like AX plus B. In that case, original X is encrypted to AX plus B. And if you put A to B, sorry, B to B, uh, B, sorry, B to be K and A to be 1, then that becomes again a Caesarean cipher. So substitution, sorry, that affine cipher is also a generalization of the your Caesarean cipher. Similarly, here also, as I just mentioned, if you put m equal to 1, that means how many coordinate you are taking altogether. If you take only one coordinate, then that becomes a Caesarean cipher. And but the point is, here the Caesarean cipher, though they are generalization of this, in case of affine cipher or substitution cipher or Caesarean cipher, all of them they were uh, monoalphabetic, whereas this one is a polyalphabetic. Because you can understand that why this is polyalphabetic, because see here O, both O was there in the plain text, but if it could be substitution cipher or affine cipher or any other cipher that we have talked about, then O will always go to O. But here look at this, here O goes to D and here O goes to W. Okay, the same plain text goes to two different alphabets. That's why this is a polyalphabetic scheme. Is it clear to all of you why this is polyalphabetic scheme? And if your
Yeah,
scheme is, yeah,
that means monoalphabetic means a particular plain text alphabet which correspond to exactly one
exactly,
ciphertext alphabet.
yes, that's why the frequency analysis works there.
And in polyalphabetic system, this will have more than one, and the pullback also have more than one alphabets.
Yes. Okay, so I think now this mathematical computation is also clear. But when it was invented, at that time there was no concept of group that usually we study using this some definition like axiometric definition of groups. So at that time there was no concept of group, but it came automatically. Okay, so as I just now mentioned, the encryption function and the decryption function could be explained by this. Okay, so there is another example of a polyalphabetic scheme, and that is known as Hill cipher. And you can understand it came quite late. It's 1929. So it's again a polyalphabetic scheme. So what is the idea here? Here idea is, suppose this is your plain text. So here idea is again quite simple. So suppose this is your plain text, say x1, x2, x3. What you are going to do, you want to do some ciphertext, right? So ciphertext y1, y2, y3 that you want to transfer. So how you can do it? If you consider this as a vector, then this is a 1 cross 3 vector. Now if I multiply it this with a 3 cross 3 matrix, then as a result I will get again a vector of size 1 cross 3. Okay, now if I use this for my encryption, the point is you must have a decryption. So how will you get, intuitively how will you get y1, y2, y3? So what you need basically to, suppose you have this, and from here you want to calculate what is your x1, x2, x3. How will you calculate from y1, y2, y3? How will you calculate x1, x2, x3?
And multiply it with the inverse of that
Very
matrix.
good. So if I multiply, if I consider this to be y and this to be a matrix and this to be x, then suddenly x will be a inverse of y, right? So the question is, if you consider a to be your key, then you can understand, if both of them they will have a, they will able to calculate both x and y. But the only thing is that this matrix has to be non-singular. So this matrix has to be non-singular. Unless you have this A inverse, you won't be, suppose this is a singular matrix and you multiply with this, then suddenly you will get some 3 coordinate here. But in that case, this guy won't be able to decrypt this, because unless he will multiply with the A inverse, he won't be able to get x1, x2, x3 uniquely. As a result, to get the unique answer, the A inverse must exist, and when the A inverse exists, when this determinant value is non-zero, right? So that's the idea of Hill cipher. What it says, the plain text. Now you can say that this is an in coordinate. So here in was 3. So plain text, ciphertext are all Z26 to the power n, and the key space is K is a non-singular matrix of order n with entities from Z26. Okay. So let us take an n cross n non-singular matrix K as our key. Now this plain text will then convert it into this ciphertext. How? This plain text, and this is my key, and this key will be shared with both sender and the receiver, and when you will get this y, you just multiply with this k inverse, and you will get x1, x2, x3, and that's the decryption process. So the question is, how many such matrices are available? So for example, if I know that suppose my k is an n cross n matrix, and each of the entities are coming from, say, Z29. If I ask you this question, how many non-singular n cross n can you find with entities from Z29? So it was Z26, right? So instead of 26, if I convert the question to Z29, how many non-singular matrix that we will get? Can you tell me very quickly? How many non-singular matrices are there of order, say, 3 cross 3? For simplicity, okay, make it 2 cross 2. How many 2 by 2 matrices are there of order? How many 2 by 2 matrices are there with entities 29 which are non-singular? Quickly, anybody tell me how
Well,
to?
29 to the power square minus 1 into 29 square minus 29 is the coordinate of GL
Very
to
good. So this question is equivalent to finding the number of elements in G2 cross 2 over Z29. And as we know, this value is this. So in our undergraduate level or in our previous maths classes, we have already calculated this, and to prove this, it requires a bit of linear algebra. So in this class, I am not going to do the same problem, but here the problem is little different. So instead of 29, if I ask you the question on 26, will that be same as, somebody joined? Okay, will that be same as Z29? If I replace 29 by 26, will the answer be like 26 square minus 1, 26 square minus 26? So that you need to think. Okay. So my question is simple question. Let us try to do with maybe 6 elements. So what is the cardinality of Z, say 2 cross 2 over Z6? So this is again your homework. So will that, so you need to think in that way, will uh, the logic be same as using GL2 cross 2 ZP, where P is prime, where P is a prime. If you are able to count or give me the exact count by some formulae, then suddenly we may try to extend it in case of 26. Okay, but anyway, there are plenty of such matrices of order uh, 2 cross 2 matrices over Z26, and so the key size is basically, that would be the key size. So what I want to mention here, I need to find this value. What is the key space value in case of this Hill cipher? So that is your homework. And to understand this, let us first try to, with, instead of 26, let's start with 6. So 26 is basically 2 into 13. That means P into Q form. So that's why I have given 26 instead of 26. I have given 6. So this is also in terms of 2 into Q or 2 into Q form. And let's try to find what would be this value, because you can try to do it on your hand, maybe few matrices, exactly how many matrices are there, that you can also try to find. And then based on that, try to answer this question: what would be the key space size? Okay, that requires little bit of mathematics, little bit of linear algebra, maybe module theory may be required a bit. So it's up to you how you are tackling this problem. Okay, but the scheme is very simple, and as you can understand that this scheme is again a polyalphabetic scheme, because suppose this x sometimes will go to, depending on which term it's got multiplied, and this same x1 may go to, suppose here again you have x1, then same x1 may be multiplied with some other column, and that may give you a different value. That's why this scheme is also a polyalphabetic scheme. Okay. So till now, what we have shown you is like this, that all the schemes that we have dealt with are basically the schemes where both A and B, they will have the same key, K, all the schemes that we have discussed about. And among the schemes, few schemes are monoalphabetic, and few of the schemes are polyalphabetic. And you can understand that in case of monoalphabetic, there could be a chance of frequency analysis, but here there is no chance of frequency analysis, is not there, but some other chance are there. Exhaustive search could be there, or maybe some other better way of having a attack system may be available here. So my question is, try to find some of the attack strategies for both Hill cipher as well as Vigenere cipher, which are not exhaustive search. Okay, so try to find some of the ways through which you will be able to find the values of either plain text or the values of the keys, because sometimes the attackers are only interested on plain text, but sometimes the attackers are also interested with k, because if he somehow able to grab the value of k, then for future transaction, for future communication, if A is again going to use K, then that will be very easy for the attacker to know what is the plain text. So you don't have to do the all the works. If he by some means he able to know the value of K, then it would be a great advantage for the attacker. So that's why what I say, that it's not always the case that the attacker is only interested on plain text, but sometimes and most of the times they are also interested in knowing the values of this case. Okay. So for these two cases also, you need to find some better way. Exhaustive search, as you can understand that if you do exhaustive search, then any cryptographic scheme can be broken. It may happen that the exhaustive search may take long time. It might happen, but suppose you are a god and you have every power to do all the calculations, then you may find that any cryptographic scheme can be broken, because it's no cryptographic scheme is beyond the exhaustive search. But the point is, how feasible is that? Okay, so you can understand that by using this exhaustive search, that means the if I have the size of the key space is here, size of the key space is 26 to the power m, And if you can exhaust all the keys, then suddenly you will be able to break the system. Now the question is, can you think of any better solution like the frequency analysis that I have already mentioned for this kind of schemes? So that is also your homework, to find some of the rules to break Hill ciphers as well as Vigenere cipher, which are better than the exhaustive search. That means you need to work less number of tries than the exhaustive search. That is
Sir,
my point. Yes. Yeah.
how can the exhaustive search can work for Vigenere cipher, because the key space and because the positive integer can be arbitrarily large, and so how can you know about the key space?
No, I have never used the whole natural set, number set, or any infinite set. As I mentioned in my previous class, that for computer science, you could have taken with J to be this set to be Z. Instead of Z26, you could have taken to be Z, right? Set of all integers. In that case, that would be infinite. But as I mentioned, to grab anything infinite, it's really difficult for a computer to implement that. Theoretically, you can always implement, but practically, it won't be possible. That's why you must deal with some finite case. And that's why we have only this P, C, and K. They are all finite set. Could be very large, but they are all finite. That's why you cannot deal with the
I'm talking
infinite
about
cases.
the exponent m. This can be very large.
Yeah, very large, but that's finite. It may
Yes, but
happen that it may take a lot of time. That's what I tell. But suppose you have the capability to run that program very efficiently. Suppose you have,
no,
then
I'm
you can
saying that
certainly break.
as m is varying, so how can the exhaustive search can possibly do all the things that I'm trying to find? I mean,
No,
in
here
previous,
aim is not varying. Here aim is not varying. This aim, you are talking about this aim, right?
yes, yes.
And that's a fixed for any particular scheme. So when you are going to do Vigenere cipher, first you have to, for example, here I have already fixed it up with 3. Here aim is my 3. So if you vary this, then the counterpart, suppose you are the sender, how the receiver will able to know that which at which point of time, which how many, what would be the length of your ciphertext or key. So that varies, right? So at the very beginning, according to Vigenere cipher, they have already fixed up this value m. So here they have fixed up m to be 3, and the password is like SIP, and he is repeating this SIP again and again. If it is a truncated somewhere, then only C is used here. If it could be X, Y, Z, Z, then CIP could have been used. Okay. So you are not varying M. So you are actually fixing M at the beginning
No,
of
when
your
I'm
scheme.
trying to attack the scheme, then how can I get the information about m? Because then m is unknown to me at first. So
Yes, but
then m
but
can be
but
very large or very small.
very large or very small, but that's also finite. You know that your search domain is finite. You start with m equal to 1, that means Caesarean cipher, then start with m equal to 2, then your key space will suddenly increase a lot. Then try with m equal to 3, then your key space will again bigger than the previous one, and so on. But whatever be the case, it will be a finite. That's what I told you, that it could be very large. A computer may not work, but suppose you have the capability to work on it, then suddenly you will be able to break it, right? So when this scheme will be started, then at the very beginning, they're going to fix this value of m. As as soon as they fix this value of m, the size of the key space is fixed, however big it may be. So if you run that many times, then suddenly you will encounter with that key what was used there, suddenly one of the element of that key space, and then you will get the answer, and you have broken it. But that's why exhaustive search is not a practical search for schemes. Like for Caesarean cipher, it may be practical. For affine cipher, it may be practical. But for other practical schemes, exhaustive search are not a feasible one. But still, if you have the ability to do exhaustive search, then every scheme can be broken, right? Because they are all finite according to cryptography. Is it clear to you now?
Yes, sir.
Okay. Okay. So this is the exercise for today. It's a Hill cipher. Okay. Okay. So let me, not an exercise. Suppose it's an example. So here, suppose the matrix is this, and you can see that the determinant value is non-zero in modulo 26. And suppose your plain text is love. So here the M value is 2. So you can encode it like LO. So the roll number for L and O is this, and VE is this. So you just multiply it modulo 26. So this is your ciphertext. This is your ciphertext. So they are your ciphertext. Okay. So it comes like 10, 7, 8, 13. And when this ciphertext will be received by the person to whom you want to send, what he will do, he will just consider this and multiply it with this inverse. And if you see that this would be the inverse of this, and he will get back the original message LOV. That's all. Okay. So here the key space size will be the number of non-singular matrices of order 2 over Z26. That's all. Okay, so this is today's exercise. So it's again a point. So you need to make a screenshot of it, and you need to answer me in my next class. So please take a screenshot of this thing, and then you read it, and then you work it out and give me the answer. What was the actual question? So it's a kind of puzzle. Okay. So in this class, I have given you many works, few problems that you need to work mathematically, few things that you need to implement by using any software, and few things that it's a puzzle. It's you need to solve it by both. So till now, whatever I have mentioned are useful for you to answer this question. So it may take some time. Okay, at the same time, I'll just go to another very interesting part of it, that is a Sage software. Okay, so it's a free available software. Those who are working using internet, so those, how many of you, so you, or not all of you might have this laptop or desktop at your place, but suddenly you can go to the internet version of it. And if you just on Google, if you just type Sage Math, Sage, SAGEMATH online, then something will come. SAGE online. Just have a look at Sage Math online. If you go that, then it will come the original page of sagemath.org. Okay. So this is the original page of this, www.sagemath.org. Okay. So here you can see that it's a download. So those who are having Windows or Linux software, they can download it and they can install it. So now the version is 9.2. You can use the previous version as well. So here there are few mirror places are there from where you can choose. For example, you choose Asia, say, or Japan, something like this. If you click here, then it will come for which software, which version or which operating system that you are going to use here. So suppose you are using Microsoft Windows, then this is for Microsoft Windows, and then there are plenty of others things are there. So you can check and you can download it even for Ubuntu as well. So you can use the Australia one, whatever you want. So here you can see the same thing. So this is for Apple OS software. So there are also for Ubuntu as well. You can find it down there. So from torrent also you can do it For Linux also, it's for 64 or for 32-bit machines. It's available. Depending on your machine, you can download it and you can install it. So good documentation is there how to install. Just you in Google, just type how to install SageMath in your operating system. It will give you lots of hints how to do that, and that can be done. So those who do not have this laptop or desktop, for them also suddenly they will have my smartphone. Otherwise, they won't be able to see my classes. So suddenly you will click here. So this is the CoCalc Instant Sage Worksheet. Okay, so this is CoCalc. So it's a basically kind of this cloud-based system where you can work on your own. So since I have already an account, so here, so it goes directly into it. Otherwise, you need to create something. So by using your email ID and password, you need to create something, and then you will get into this thing, and there you can work your own worksheet and so on. That I will come to you later on how to work on it. But before that, please just try to do it and do it because it gives you lots of advantages. For example, suppose here I have uh, things like, for example, if I go like this, it will give me, okay, so it's a nice software through which you can do lots of things. Like here it's a kind of animation that you can do. So it's a sine 1 by x. So we know that how the sine 1 by x looks like. If it goes nearer to this y-axis, then it oscillates more. And you know that what is the status of its continuity or uniform continuity and so on. So it's a kind of animation of sine a by x where a varies, and you can understand that in the origin how it moves, how oscillates. So there are plenty of such things that you can do. Here you can move it. So maybe next day I will show you how you can do it. Uh, yeah, so you can change the name or you can even move. So you can see the lightings. So the places where the light reflects. So it gives you an accurate source of light and all. So it's a huge software. So many of you might have used Mathematica and MATLAB, but you need to pay a lot for that. But here it's completely free, and it has a nice this kind of documentation. So anybody, so you can have a matrix and then you can solve a Sudoku even. Okay, so it's a Sudoku. I have given a puzzle Sudoku input. I have given an input and gives you back the output of the Sudoku. So it's a like sine curve, and you can do this for real analysis studying. It's really a very good tool to teach as well as to understand how the curve looks like. You can make the curve and all. So it's like the curve, and it is the derivative of the curves. So you started with a curve and then started derivating. Suppose you have started with a curve and then started derivating things and how the curves changes. So I started with this, and then I started derivative of h, and then again derivative of, so this is f is the derivative of h, then g is the derivative of f, and so on, and then plotted how it looks and how it changes. So it's a nice thing that you can change the color for different curves and all. So it gives you the idea of series, sequence, etc. For in case of a series, in case of a sequence, how it looks like, how the points are convergent means what, etc. That any neighborhood can contain infinitely many of things, and this is a kind of convergence series and all. So everything can be worked out here very easily. Like for graph theory, you can draw graphs, you can find the adjacency matrix, you can find the characteristic polynomial of that curve, you can find the eigenvalues very easily, you can find GCD, you can find have a big numbers. For example, suppose I want to find a prime number. Okay, for example, suppose I want to find prime number, next prime. So it will give me output as a next prime of say 100. So suddenly it's 101. You may think that 100 is too small. So why not make it 2 to the power 100? And it gives you readily this answer. So this is the next prime of 2 to the power 100. So you may think that okay, 2 to the power 100 is too small. Why not 2 to the power 1000? So it will, you can understand that it will take some time. When it will calculating, it gives you a green color here and it gives you 2 to the power 100. So it will contain around 300 digits. But if you want to make a factorial of how much you have seen, say 10, you can check easily how many zeros are there. You may think, okay, why 10? Why not more? So 100 factorial is this. So you may think, okay, 100 is too small. Why not 1000? So it's a 1000 factorial. If you say that, okay, 1000 factorial is too small to me, so why not 10,000? You put another zero and it will give you the answer. The full text is this. And within a fraction of second, it gives you the answer. Now you can calculate how many zeros are there and you can check with your mathematical argument that, okay, this many zeros are there and so on. So using this, we can do plenty of things. And by using our, say, for example, here I was calculating the point how many non-singular matrices are there of say order 6. So order 6 is, so they are all non-singular matrices and the count would be ultimately 966. Okay, so you can check with your mathematical argument whether this 966 are there. Now you can see that how easily I did this. So I have taken n to be 6 and count to be 0 and Zn is Z modulo n and that's all. And here I have given n and I put the value of n to be 6. Okay. Z modulo n basically gives you Zn. And now for A in Zn, that's what? Very easily, A in Zn. A starts from 0. In Zn means it will be like first element is 0 element. Then again I go to another for B in Zn. That means it will give me another element of Zn, C in Zn, D in Zn. That means first element it will check with 0, 0, 0, 0, 0, 4 zeros, A, B, C, D, all zeros. And I said that if AD minus BC is not equal to 0, and that this 0 becomes an element of Zn. If it gives you not equal to 0, then ultimately it gives you this value and so on. So you can check very quickly. Can you tell me what is the value of, if I consider Z, if I consider Zn to be Z7, that means what is the cardinality of ZL2 Z7? Can quickly tell me what is this value? This will be 7 square minus 1 into 7 square minus 7. Now tell me what is this value? So this is 48 into 41, right? Quickly tell me what is this value? Quickly, everybody. So this is, I think, 42, right? 42, not 41.
It's 2004.
2004.
Yes.
Okay. So let's check how this calculates. Okay, if I,
2016.
okay, let's see. I'll just check like this. 7 square, 7 square minus 1 car. 7 square minus 7. And what is this value? 2016. So who gave me this answer wasn't correct. Anyway, so that's the point. I mean, we need to be little careful while making this calculations very fast. So that's the answer, like 2016. And let's put here the value 7. Let's check whether the programming works properly or not. I have given already in value to be 7, and let's check how it gives me the answer. And let's check, and 2016. Okay, and it also came 2016. And you can check all the matrices if you are interested in. You can see all the matrices. So this is A, B, C, D. That means this is 0110. So 0110. It starts with 0110. So its value is -1 in Z27, Z7. That means actually class 6, and so on. So nicely, you can very easily, you don't have to code much. Using this, you can do whatever you want mathematically. Very sound, very good documentation is also here. So you must read, or you must write things in Sage Math. So that will also reduce a lot of your pain when you start writing in C programming and all. So in this course, I will also teach you a bit about it. So please try from your mobile or your desktop or your laptop to install this, or from your laptop you can, or your desktop you can install it, but from your mobile you can have to do it like CoCalc in this, like this. So it would be, you can understand, it would be quite slow. It depends on your mobile and all. It depends on your internet speed as well. So maybe I will check some how much it takes time maybe. Okay, let's see this one. So you can understand that it will be less powerful because it will take some time, but let's see how much it will take to calculate this 7. Then you will be able to compare it. So it's not yet giving. The green color means it's giving your answers. You can see that it has started printing all the matrices, but green color means it's still printing, still working. So I got the answer maybe within 10 seconds, but here it's still working. So because you are working on a cloud, so it's, my machine is connected with the cloud using internet. As a result, it will be little slower. But at least you can at least work. You can have the feelings how it works. So you can do it by using this. So it has given you the answer 2016. Okay. So we'll stop it. Yeah. Okay, so here I think the green color means it's not working. It's always green means it's the output zone. Okay, so it might have given you earlier answer, but still it will be less. It will take more time than your local machine. Okay, so in the classes we will also have a look at these things with more detailed, and we'll work on it. So any question till now, if you have? So if not, then we'll stop here.